Hi, Science 30. So this is going to be our first video in our physics unit. We're going to begin with a discussion of field theory. So in field theory, we're going to start with gravitational fields, but we'll move on into electric fields and magnetic fields. And pretty much when you talk about field theory, a lot of the basic premises all stay the same. So in general, no matter what field we're talking about, a field is an invisible region of influence that causes other objects to experience a force. So what's a force? Well, a force is that classic push or a pull. And so pretty much any field that you are studying, you can sort of indirectly see or indirectly observe by looking at its effects on other things. And so if something else is being pushed or pulled or interacted with in some sort of field-like manner, we can say a field might be present. So like I said, we'll study three types of fields: gravitational fields, electrical fields, and then at the end we'll talk about magnetic fields. We'll talk about calculations for two of those three. And even the calculations stay very, very similar. So although Earth's gravitational field is present, you can't see it. But we could draw a field diagram and you could sort of explore how the gravitational fields might look in Earth's circumstance. So the lower concentration of field lines indicates that their field is weaker out here. So notice how there's there's more space between the lines out further away from Earth, and if I kept drawing these lines out, the space between them would get larger and larger and larger. And so here, let me see if I can draw in here with you. I am going to, so if I were to extend this line and extend this line and extend this line, notice how the space between these lines has gotten larger. So the further away you get from Earth, or anything with mass, the less the gravitational energy is. Notice how the closer you get here, the more close together the lines are. This means that there is a higher concentration of field lines, indicating there's a stronger gravitational force closest to the Earth's surface. This is why as soon as an asteroid gets pulled into Earth's gravitational field, we have to look at it and watch it closely, because the closer it gets to the Earth, the more likely it is and the faster it will be that it gets yoinked in by Earth's gravitational field and then plummets to the Earth, possibly causing a lot of damage. Okay, so with that being said, I'm just going to continue on here. So example of gravitational fields would be like things falling to the Earth orbiting the sun. And in this unit, we're going to talk about test objects. So a test object is anything, in this case, that's going to show us that there's a gravitational field present. So the test object in a gravitational field scenario is anything with a mass. If it weighs something, it can be used as a test object. In electrical fields, static energy and lightning are examples of electrical fields, and a test object would be something with a charge. And then in magnetic fields, anything like a magnet or a compass is going to show a magnetic field, and a test object here would be a magnet, something with a polarity. So field line, or in physics you might call these vector diagrams, tell us the direction and the strength of a field. So the field lines for gravitational energy look like this, where the ones closer to the object are closer together, meaning there's a stronger field strength there, gravitational field strength. In electrical fields, we've got positive and negative charges to work with, which we'll explain in the next video. And then we've got magnetic fields, where it's very similar to the electrical fields, but we're looking at polarities and magnetic charges. Okay, so gravitational fields. So gravity is basically an invisible region of influence where a force of attraction acts to pull a smaller object always towards a larger one. So gravity moves from small to big. And so big things have more of a gravitational field strength or a pull, and smaller things get caught in that pull. So that's why when I take this pen and I drop it, it goes down to Earth, because the pen has a small mass and the Earth has a large mass. You have a relatively small mass compared to the Earth, obviously, which is why you stay on the ground. If you jump, you'll fall back to the ground. If you were to jump off a diving board, you come down to the ground. You don't go anywhere else because the relative mass is much less. of you than the Earth. So the Earth has a strong gravitational field strength pulling you in. So gravity is an attractive force only. So you wouldn't fall away from the ground. You always fall towards it. Gravitational field strength is attractive only. So the gravitational field strength around the Earth. So where is the gravitational field strength the strongest? Well, it's always going to be strongest closest to the Earth, and it's less strong further away from the Earth. So just above the Earth's surface is where the gravitational field strength is going to be the strongest. Now think about it. The moon has a small mass compared to the Earth, so the moon is going to orbit the Earth, and it's going to orbit the Earth weakly. And so since it's not a very strong attraction, it's because the moon has a smaller mass than the Earth, and it's going to orbit the Earth, but then the Earth itself has a small mass in comparison to the sun. So notice how it is orbiting our sun. So both the sun and the Earth are capable of producing a gravitational field, but because the sun has a larger mass, the Earth is attracted to and will orbit the sun. And so we can use gravitational field strength as a mathematical representation as well. So this is a formula that you do need to know. Now, I've linked the data booklet into your Google Classroom as well, and so you would have access to a digital copy, but you all should have a paper copy as well. And this is a gravitational field strength formula. So the gravitational constant is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That's big G. That's a gravitational constant. It's never going to change. The next number is your gravitational field strength. This is like the field strength that you're calculating. What's the pull? What's the pull that that object has? What's the gravitational field strength? Little g. Don't confuse little g up with big G. Big G is the gravitational constant. It's never going to change. That number you're going to find in every textbook and every Google search ever. But little g is going to be specific for your object. So it's the magnitude of the gravitational field strength. So how much the pull is. And it's measured in the units Newton per kilogram. Little m is the mass of the source, so the biggest thing present, measured in kilograms. And radius, r, is the radius or center to center distance measured in meters. And in this formula, we square this number. So some formula questions here. What happens to the gravitational field strength, g, right, if mass increases? So if I increase the numerator, then I'm going to increase the gravitational field strength. Now think about it. If my object gets heavier and bigger with a larger mass, then it's going to have a larger field strength. Makes sense. What happens to the gravitational field strength if the radius increases? So if our object is further away from your source, then it's going to have a smaller gravitational field strength, which makes sense mathematically because radius is a denominator. It's at the bottom of this fraction. So the larger the denominator gets, you're dividing by a larger number. And so you are going to decrease the value of g, of little g, the gravitational field strength. Okay, so your data booklet has a page that looks like this, and so it's got a number of formulas, which we may or may not use throughout the year, and a bunch of constants. And so a constant that we're interested in is gravitational constant, and that's that 6.67 times 10 to the negative 11 Newton meters squared kilogram squared. So the shape of your graph is always going to be an exponential decrease the further away you get from the object with the heavier mass. So this is a gravitational field strength versus distance from the center of Venus. So as you go further away from Venus, so distance from the center of Venus on our x-axis, as I get further from Venus, the gravitational field strength, or little g, is going to change. It's going to decrease significantly. So the further I go from Venus, the smaller the field strength is. Okay, so here's a example. In Science 30, you must be able to determine the mass and radius affect gravitational field strength. So use the following table along with the okay. So there's some information here. If we look at the equation, g is equal to gravitational constant times mass divided by radius squared. Can g ever change? No, it's a constant. What if m increases? Well, g is also going to increase since m is a numerator. We already talked about that. What happens if r increases? Well, r is a denominator and radius is measuring how far away from the object we are, so it makes sense mathematically that if r, the denominator, increases, we'll divide our total value by a bigger number, our g value will get smaller. But physically, that makes sense too, because the further away you get from your object, the less the gravitational field strength is going to be because the object is going to get further away. So I'm going to do an example with you, and let's see if we can follow through together here. So, okay. In this example, it reads, calculate the value of the gravitational field strength at Earth's surface. So that's all it gives us in the question. It didn't give us any numbers. So your data booklet has some set information that a question might ask you. Well, first of all, it gives you the mass of the Earth, 5.98 times 10 to the 24 kilograms, and it gives you the radius of the Earth, 6.37 times 10 to the 6 meters. So we're going to need these two to find the gravitational field strength at Earth's surface. Okay, so we're going to set up our question. It's always good to have a picture, list your variables, show your work, and then identify your final answer. So you're trying to find gravitational field strength G. So we know that the mass of the Earth from the data booklet is 5.98 times 10 to the 24 kilograms. We know that the radius, thanks to the data booklet, is 6.37 times 10 to the 6 meters. And they want us to find little g. I'm going to start plugging things in. So big G is a gravitational constant, also from the data booklet. It's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. I'm going to multiply that by m, the mass of the Earth, which was given to me in my data booklet, 5.98 times 10 to the 24 kilograms. I'm going to divide those by r, the radius of the Earth, which was also given to me in the data booklet in this case. And it was 6.37 times 10 to the 6 meters. Now I can't forget that in my formula it's asking me to square radius. So I'm going to have to square this. If I'm using a TI-83 calculator or a graphing calculator, I want to make sure I use my brackets properly and just square the r value and not square the whole thing by accident. So now if I'm doing this by hand, I can start crossing out units, which is a good habit to make sure you've done things right. So meters squared cancel with meters squared, kilograms are going to cancel with kilograms. You're going to be left with the units of newtons and one set of kilograms left. So you're going to have an answer of 9.82 newtons per kilogram. And you round that to the total significant digits, and you have your final answer. Okay, so in your notes package, you have a couple questions that all basically use that exact same formula, and they might ask you to solve for different parts of it, but it's, for the most part, very, very straightforward. It's plug and play into this formula. So some hints here for the questions. If you're looking at example 1 in your notes package, keep note of this purple box here of hints. Example 2, a little bit of a hint here. I'm going to move my webcam over so that you can see. Just got to get rid of this. So use the mass of a larger object that is producing the gravitational field. That's the hint for example 2. Example 3 gives you a hint, you have to rearrange your formula. And example 4, you have to rearrange your formula to solve for r. Okay guys, so that's gravitational field strength. Feel free to do some example questions in the notes package that I've listed for you on Google Classroom. Next we're going to work on electric fields and then magnetic fields. And then we're well into our physics. Thanks guys.